here that you can do on your own. Download for South America. Here. It should be a zip file. You can save it to your computer. I'll kind of show you what it looks like in QGIS, just so we can all visualize it. Here's our map that everyone should have. Okay, I'll give everyone a second to catch up. Okay. And I'm just going to navigate to this this shapefile that I downloaded. So I just put it onto my desktop here. Okay, desktop. And here's my hydro sheds. So I know it's a little small, but hopefully people can see, and on the side screen as well. This is where I saved my file to on my computer's desktop. And you'll see that the hydro basins has different levels, levels 1 through, I think maybe even 16. And the higher the number goes, the smaller those basins goes. And so they kind of keep making smaller and smaller catchments. So we can just take a look at a couple of these if I double click one. So this is what the level 3 would look like. And then if we were to pick something like level 7, they get very small, right? So this exercise, it's super basic, just getting people more experience with QGIS, with Jupyter notebooks, and getting more experience adapting the scripts and getting used to that. So all we did, I'm going to remove one layer here. I think we did level 5. 5, okay. And what Sean did was to pick one of these basins anywhere you want, as long as it is within our Cuenca da Plata shape here. Oops, I'm going to drag this to the top. Okay. So I think Sean chose that shape. And you can pick any one you want, and then you can save this as a shapefile, and I'll show you how to do that. So your download. Okay. Is everyone question?
Where is the file?
The question is, where is the HydroSheds file? It depends where you download it onto your machine. So I put it onto my desktop because it's easy to find. It may be in your downloads folder. If you go, where is the file on the website? I understand. If you scroll down here. Okay. I think your products and hydro basins should be there. Okay. Yes. Okay. Yes, we have a question online. Yes, we had a question from the Zoom. Is it possible to use a local shapefile if you have one on your computer already? And the answer is yes. We're just showing an easy way to get shapefiles if you're not used to working with them. Okay. So I will, well, what I'll do here, I think in the interest of time, we'll just show you kind of what we did once we have our shapefile, what we did to the script. I feel like maybe I should take a second to wait. I should take a second. Okay. You already have that. And what you'll do Okay. Let me, how about this? I will very quickly look at the code. And then once we look at the code, see what we changed, then we can go around the room and help people. How about that? Okay. So yeah, we'll get there. Thank you. So all we're really doing here is we've created a new Jupyter notebook in our folder. Okay. I'm looking at my files here. And this is our folder here, data. So session 2B, soil moisture, access, and data. This is our example that we chose from HydroSheds. And you can replace that shapefile with anyone you want on your computer or anything that you downloaded. And once it's in there, you can go back to the code itself and find the name of that shapefile. So I'm actually just going to search for shape. Here it is. I think it's on cell 10 in the Jupyter notebook. And you can just change the name to whatever you want, right? And it should run just like Vencat's code did. It'll use the same data as Vencat's code did, the same SMAP, the same GPM, but the plots will be different, right? So this is just a very simple example. Well, I know. I think so. And then also the time series at the very, very bottom here. Okay. Around. Okay. This was just wanted to show the code, and now we can answer questions in the room and online. Okay. Yeah. Okay. Question online from Michaela. The path for the new shape will have to be ISAT training La Plata. Yes. Yes. So for those online, just over lunch, we changed some of the stuff on the GitHub. We pushed new files. And so we're asking that everyone does a Git pull. So they get all the new folders. And once you have the new folders, I'll pull it up here. You'll have this folder now. And then it'll have a data folder on the GitHub. And that is where that's where the current shapefile is. And that's the file that you would change with your own shapefile. Okay. One more question here.
Another question from Camila from the Zoom. Is there any way that we could download the files from the QGIS project? She has not been able to connect the JIT to Anaconda. So is there any way to download the shape file and do it from scratch with GIS? She's having trouble.
Yes.
Download it from GitHub.
Yeah. So the question was, do we need to use Git? To some people, I think it may seem like a headache, maybe. The answer is yes, you can just download from GitHub onto your computer. The only problem is that you won't be able to do a pull afterwards. You won't be able to kind of update that folder in real time. But what I would suggest, if people are online having issues with GitHub, you can wait until the workshop concludes. At that point, all the files will be finalized. We won't be changing it throughout the week. And then you can download that final repository to your machine. I think that might be the easiest thing.
After you finish working with the house.
Select the basin and running.
Hey, you know what you say after you finish your GitHub activities? Hold on, man. Got her. Just say got her. After you finish your GitHub, it says got her. You get it?
So yeah, and this is an answer to your question after the answer to your question after you have the new shape file. In this section that says subset and reproject the SMAP SM data in the watershed. This is where you put in the new title for that. Yes.
Thank you.
Taking a lot of photos. Did you get some good ones?
Sorry?
Okay, raise your hand if you have if you're stuck, if you have a question. Not you. I know you have a question. You good? That's it. I was still running.
Yeah, yeah, I don't know where to find the banana. To less shape. So you can use. So I don't know this. Question. Right. No, you want to say yeah, that's the way to do it.
Yes, there are two. One.
Is there a way? That was created. Okay. Yeah, so are you gonna respond with text?
You just need to use this one actually. Let me. And you can use that one.
the name and then script the trivia.
Yes.
Yeah.
You'll change the name in the script. Actually,
Change to whatever.
Oh, name, change the shape by name. Okay, okay, okay.
Hey, John, somebody asked a question when you had gone out, when I was giving my talk. Is there a follow-on to the GPM mission? I don't know. I said, if anybody knows, you would know. I don't think, I've never heard about a follow-on to GPM because it's reaching also the end of its rocket fuel time, so.
No, I got stuck here, then I had to restart the kernel. But, yeah, I don't, it takes a lot of time.
Counting down. Counting up.
Down. I put that file on the. No, just where. Here it was. Yeah. Yeah, extract from the QGIS from this part, extract the survey, and I put it here, then I change it.
See, Mira, you don't know where path on SHP comes from? Yeah.
I think
Yeah. Has anyone got it to work yet? But just. My question for you is, we don't have to write the path SHP, that's the existing path. The only thing they need to hardwire and edit is the name of that file.
They put their shape file in that folder,
Which folder?
the data folder.
It's the data.
Change the name
Change the name to what?
to the name of the shape file. I didn't get a chance to. I didn't get a chance to add, like, to really test it out. That's kind of why.
But
Okay,
so
so,
people are happy. It's good.
all right, as long as they're happy, because I'm getting a lot of questions.
I did, I wanted.
It's just like. It's not working.
Trying to. Did it work for you?
For me, but we are sharing, we are testing, instead of a shape file, a KML, right?
Okay, okay, but it did work.
Yes.
Okay,
It did work with different basins, we did that, and now we are testing a third basin, but in a different form.
okay.
I don't know why. I upload the. I've already. Update. Maybe I restart the computer or something like that.
You're gonna have to ask.
It's something with the library, but well.
Yeah, okay.
Very difficult. Failed. Yeah,
It's
probably, I don't know.
yeah, same for me too. What time does your session start?
Well, we could start.
So being careful. What do you think?
Which part's not working?
I mean, it's all different.
Most of the people were able to finally get through the Jupyter notebooks.
Yeah.
So at least the ones that I saw. There were a couple of their own problems, they've got to start the environment.
Can we make sure Juan Carlos works?
I'll try that. We gotta get going. We have to get to John Island this time.
Okay. Should we get started? So. Line 6.
No, just the. Sponsoring hip hop. I saw sections to be two.
John, and you were telling me last night, it's too simple. I think we have accomplished. That's okay. It'll reach everybody.
Yeah, because my, all my give what's the very.
When you say that, you're.
I don't know. I was looking at it.
We didn't define.
So he changed the SHP, then he saved it, You run it. and
I know what the error is.
Here,
Because that 5 must be 5 years.
this line,
Now it's 2, it's 2
the
years.
same part, the back,
Yes.
the body. is,
Look at that. NP
Fine.
Lin space,
uh,
2020, 2021, it's only 2 years.
Find.
Or 1 year, however you call it. So I'm pretty certain that in the previous code, which Ben wrote, it was 2016, 2021 was
Right.
5. And this is 2.
We all tried that.
Yeah.
You know what I'm saying? It's a duration.
Okay.
I don't do programming. I can figure out.
I'm an anthropologist.
Huh?
I'm an anthropologist, so, you know, it can be.
Very good company.
I found the solution. No way. Yeah, in QGIS, I selected the basin. Export, but I didn't select export selected basin. So it's for, export all the catchment of South America. That's the reason why I start to, I can make a loop or a basin.
Yeah, see, go to the original one. NP Lin space, no, where it is. Where, show me. That's why it's 6. So this should be 2. That should be 2, bro. The 6-year name, he's using 2 years. So it should be 2. That's it. That's the answer. Can you email that person? It should be 2 before D type integer. Yeah, just try 2. You see, it's using 2 years. That is using 6 years. 16, 17, 18, 19, 20, 21. Yeah, that's correct. Just change it to 2.
All right. If you can hear the rumble in the room, that's science. That's science happening. That's progress. If you can hear that. So raise your hand if you got this to work. Okay. We have two successes. How many are this close? Maybe. So there we go. With 3 people get it to work. So technically we're scheduled for a break. You guys got it as well? No? Yes, okay. So we're scheduled for a break right now, and John Islander is going to close out the day with a different flavor of exercise. Do me a favor, if you did get this to work, talk to your neighbor and maybe share and help. We're here to help. But what we're finding is that everyone's environment is different on their laptop, and that's a challenge. Yeah. Yeah, okay.
So.
I said.
Okay. John, how much time, when do you want to start? Okay, so if anyone wants to take a break, we're going to get started with the next exercise at 4 o'clock with John. So we can revisit this. I'm sorry that it didn't work out for everyone, but some folks got it to be successful. So this is why we're here. I think, yeah, this is the fun. See, you're still smiling. That's good. You're still smiling. Share all this. And you've had the hardest time. Yeah. Oh, this looks like you got this to work. No.
No, hasta esta mañana todo bien.
We can find the shape. Yeah.
You did find shape. I don't understand. Like. When you did. We did that. Eran los datos originales. It doesn't work.
With the same.
Right, did you try reset? Reset. Reset. Start from the beginning. Start from the beginning. Sometimes we have to run. Step through. Keep running. Until you can, So, basically saying it's not find the shape file. Okay. So probably doesn't have. It's the shape. It's the variable, it's not. So, but I thought it was the shape variable should have been set up earlier. Where is that shape? Right.
That's the direction.
Okay, so it's there. So here's the shape file, right?
No, este.
So it was opening in shape. Problems getting that from here. To the later. If it couldn't find the shape file, it would have errored on open shape file. Okay, so what it errored on was the get layer. And so the layer that we're trying to list, I'm trying to do is get the layers that are in there. So we're failing on the list. Still. Move this window over. Just drag the window. Hold it. Someone move the hand. Go back to the directory. Yeah, that's right side.
You didn't make a change in your. Did you make a change to the code? Okay, so it's standard, so it should work. Okay, hold on. Looks like it's fine with the file, but then he gets an error on the list command.
Back here. No, you're right. Oh,
Yeah.
So then, that's been two. Now. That's why I said that.
an observation type guy, go out in the field, plant a few sensors, take observations, go home, write about them, PhD work, right? But I chose the computer coding, and which is frustrating 99.9% of the time, I think. And then the rest of the time, it's a great adrenaline rush. It worked, right? So, okay. So we're going to talk about, we're going to switch gears a little bit. We're not going to talk about the evapotranspiration now. We don't have time tonight. So we're going to talk about a topic that's a little shorter. And so I hope that you'll forgive us that we're switching the MOGWI talk, the Modus Optical Global Water Information System talk, to today. And we're going to talk about evapotranspiration in the morning, because I think you need to be well rested for that talk, because there's some physics involved. This doesn't have nearly as many physics. Okay, so I think those of you who have been staring at code, you probably don't want to deal with physics right now. So we'll leave the physics to the morning. Okay, good, good. Am I talking slow enough in the booth? I got the thumbs up. Great. Okay. So we're going to talk about using MODIS data. So I'm a modeler. I'm not a remote sensing person. I've done remote sensing. It is one of my jobs when I worked also at NASA for a couple of years. I'm very familiar with remote sensing. My master's degree actually was in remote sensing, but since then I went to the dark side and I've been a modeler. Okay. It's a disease, you know, it kind of grows on you and eventually it just takes over. But I use a lot of remote sensing data in our modeling system. And so I have to have a very deep understanding of remote sensing so that I can use those observations in models. And that's what I like to do, which is couple, you know, satellite remote sensing observations into models. And the tool that I'm going to show you today, or the algorithm, the application that I'm going to show you today, is one of the applications that we implemented jointly with some of our colleagues at USGS and other places, so that we can actually take the observations out and use it in our hydrology models. Okay, so we didn't really have much of an interest in using MODIS data because I work for the Army Corps and we're not a remote sensing center, but I'm interested in the output because it's a hydrology product that can be directly used in a hydrology model, which is reservoir or lake area. Okay, so earlier, somebody was asking the question about, you know, how do you get, you know, the volume of a lake from remote sensing data? Well, this is one of the ways. Okay, we can measure area of a lake from satellite imagery. And if you understand your lake bathymetry or your reservoir bathymetry, then you can combine the bathymetry to get that volume of water that's in your lake from satellite. Okay, so we'll talk about that. Where's my slide driver? I guess I'm driving slides. Okay, so MOGWI. It is a really bad acronym. That's the first thing to know about it. Okay, engineers are really bad at acronyms. This is a really bad acronym. Okay, Modus Optical something 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 information system. Okay. We did not develop the methodology. Our group and the Army Corps did not develop the methodology. We, I don't want to say we stole it because we didn't. We partnered. That was the polite term. We partnered with another agency, and it was actually John Jones from USGS. Okay, so the method was developed by USGS, and here's the two papers that describe the method. And when he developed the paper, it was called DSWE, Dynamic Surface Water Extent. Okay, and he developed it from Landsat data. But since we needed a rapidly more updated capability, we modified it with USGS to use MODIS data, and that's what we implemented. And we actually run this algorithm in real time with the data that we get from USGS that you now know how to get because The links are, you've already tested some of that. You have a Earth Explorer account. So today earlier, as one of the exercises, some of you, how many actually got the Earth Explorer account? Okay, a few of you. Okay, good. So if you got the Earth Explorer account, then you have the ability to download the data that goes into this algorithm. Okay. So, and for me to do this demo, up until this workshop, I didn't have slides or anything that describe what we do with this tool. I had to create them, and I had to go and create the demo myself. And I had to, for the first time, create my own account on Earth Explorer. So I just went through this recently myself. So I know it works. Okay. All right. So, but these are the papers that if you want, go grab from the internet. I think most of them are open access free. I believe these two are. Actually, all three of these are. This third paper here is actually the manual. So the algorithm that I put in this paper actually comes straight out of this document here. Okay, so all I did in my slides was summarize this document here. It actually will tell you almost exactly how to code it. It doesn't give you the code, but it would tell you almost how to code it up if you wanted to code it up yourself in Python. Okay. All right, so it wouldn't be too hard. So quick aside, okay. How many people, we did this before, how many people already knew how to program in Python? Okay, a couple. So other than like Google, what's the second best way? Well, no, it's actually the first best way to learn how to code in like a new language, Python or, well, trial and error, or YouTube, but actually the best way to learn how to code is to get somebody else's code. Okay, it really is. Because once you get somebody else's code, you can start reading that code and understanding the syntax of how to do stuff, right? So today, what did we give you? Somebody else's code. Okay, so you all have Jupyter notebooks, which is basically just a nice way of putting Python in there to run interactively. You have somebody else's code, you know the syntax. I'm going to give you an algorithm. You could code this up yourself and have it running by this weekend. So there will be a test on Monday. I want you to email me if you've got this running. Okay? No? No, okay. All right. So, okay, we'll give you till Friday. Okay, what is Mogwai and how does it run? So the goal is to calculate the area of a water body in essentially square kilometers. It works for fairly small water bodies. Okay, we're using MODIS data. And for the most part, we're using the 500 meter product. So, 500 meter grid satellite data, it won't work for the pond in your backyard or something like that, but it works for a decent size, small lake. Okay, so, and there are a lot of lakes around the world that you can apply this algorithm to. And I'll show you a map of where we have some, okay? The way it's calculated is it's actually about a 4-step quick little algorithm that's very easy. It uses this algorithm called the Modified Normalized Difference Water Index, MNDWI. Earlier, we talked about NDVI. Okay, which is how many people, other than in the Jupyter notebook, how many other people have tried to calculate NDVI on their own using SAT? Okay, a few of you. So it's a fairly simple algorithm, right? It's 2 channels subtracted, it's blue, green, subtracted from each other, divided by blue plus green. So it's a very simple, band math algorithm that you can apply lickety split. Okay, it's very, very quickly, as long as you know how to read the satellite data in. QGIS is great for that. So we're going to try to, if I have enough time, if I stop talking, we'll give you that quick little demo. Okay, so and DWI it's slightly different channels, but it's the same concept. It's the blue minus the shortwave infrared over blue plus the shortwave infrared. Very simple to do. Okay. Then we calculate a couple of other tests. There's the partial surface water extent tests, which add in the near infrared and a couple of other thresholds. We'll take you through that. And then there's there's partial surface water extent, and then we actually have to read in the NDVI product also. Okay. This product, when the USGS developed it, it was initially engineered to work in the Florida Everglades. Anybody ever visit Florida and go to the Everglades and see all the alligators? What are the Everglades like? Is it a nice big pond or a big lake? It's covered by vegetation, right? Yeah, so it's completely covered by vegetation, which is why these tests are important, because it takes the vegetation into account. So there's a couple of parameters that deal with that vegetation. So the goal of the Mogwai algorithm, or DSWE, was to map not only just pure bare water, but to account for water that might be in partially vegetated or shoreline areas. Okay, so that's all this algorithm really does. It's very straightforward. Again, we run it in Python code. Okay, and when we run the code, there's about this much section of the code. Literally, it's only about this long that actually is the algorithm. And there's about 500 lines of, okay, go get the file here and read the file in, make sure the file's in the right, all the data handling is the majority of the code. The code is very short. So it's not complex at all. Okay. So when we run this, our goal is to monitor lakes, all around the world, and just look for areas of drought, look for areas where, that might be flood prone or where it is flooding, from a global awareness perspective. And then we can take those products. If I'm running a global stream flow model or a stream flow model for a very large watershed that has multiple reservoirs in it, I can use that lake area value as a parameter input into that model to help with the calibration of my hydrology or hydraulics model. Okay, so that's why they become very, very important. Okay. Yeah, and so that's when the bathymetry becomes really important. So if you want to get to that next step, you have to have your bathymetry. I don't have bathymetry for most of your rivers down here. We can get it, but the bathymetry becomes important. So that's the background of the algorithm. All right, other than the data. So the products that we read in, there's two different Modis products you can read in. Q1, which is the 250 meter product, or this A1 product, which is the 500 meter. Okay, the 500 meter has all the bands that we need. You can also combine the Q1 and the A1 product together if you want to do it at higher resolution. I'm not going to do the demo at higher resolution. We're just going to do it using the Q1 product. Okay. So additionally, I'm not going to do this because it takes a little bit longer. And because there's no snow down here, okay, if we did this up by me, there's snow, we have to deal with it. I hate snow. I also chose a cloud-free scene, so we're not going to deal with clouds today, okay? But you do have to do it in an area where there's no clouds, because if clouds are in the image, you can't see the water. That's a bummer, but it's real, okay? So you have to account for clouds and snow mask products. I just chose a clear scene, so we're not going to deal with that. Okay, and then here's the process. All right, so the algorithm is, I think, on the next page. This is the algorithm. All right, what I didn't give you is, once you create the mask, the last step is in your GIS program is you have to essentially go around and calculate the area of all the pixels that were clear, or that were water covered. Okay, I'm not doing that as part of this demo. That's a GIS exercise. If you know the relative area of each one of those water pixels, then it's just easy to add that up and say, okay, my area is 500 meters by 500 meters. Okay, and then that's how you get that area value. This is the actual what we call the spectral tests that you have to pass. And I think that's more important to anybody, because that's how you get to the point of saying, hey, I'm going to play with this, is to understand the spectral test. Okay. But again, here's the modified normalized differential water index product, which is green minus your SWIR channels, shortwave infrared. then green plus, divided by green plus SWIR. Okay, so that's actually the biggest test. Very simple algorithm. The next thing is there's two partial surface water tests, and it's actually the same test with slightly different thresholds. And the reason we do that is just there's a conservative value and a non-conservative value. Okay, and so we're just playing with the thresholds to make sure we're teasing out all the water right. And then we compare the green and red bands a little bit, and then we add up. We basically say, okay, after we pass all those tests, based on where the water is marked in each one of those tests, we just add up all those pixels and we calculate the area. It's very simple. Okay. So this is straight out of that manual. These are the thresholds that was in the manual. Okay. So if there's a threshold value, so once we calculate the NDWI, this is the value that they had in NDWI. Our value is actually 0.144 for MODIS. This one's for the Landsat value. But some of these values you can play with also, depending on if you want to tune it for your own purposes. Okay. So anytime you see a value like this, that you can actually modify these, and feel free, play with it, do science. Okay. Most science occurs when you just say, hey, I want to play with that, see what happens. Okay. Here's the other values that we also include. So this pixel value here, what we've done in the code, when we run the Python code and we say, okay, I'm going to calculate my NDWI, at the end, if there's a value in each pixel greater than this value, then we give that pixel this value. Okay, so which really, when we give the pixel that value, all we're doing is we're setting a flag. Okay, so we're basically flagging that pixel as having a 1. And then if this test is passed, we give that pixel, we add 10 to that pixel. And if this test passed, we add 100 to that pixel. So by the time you're done, if all 3 of these first tests pass, then the pixel should be 1, 1, 1. That basically means that we passed all 3 tests. And at the end, we have a little if loop that says if pixel value is 1, 1, 1 or something else, water. Great. Okay, fairly easy to do. Okay. Same with these tests. So again, it's just, if we pass this one, then it's 1,000, and then this one is 10,000. Again, we're just labeling each one of those digits as a flag. Okay, and then there's a bunch of kind of if-then tests here. Okay, if these are passed here, then in reality it's probably not water. But if you get 4 of the 5 tests, then it's probably water. So this is just our matrix. Okay, fairly simple. Okay, so the goal at the end is we're trying to identify water. All right, and anybody recognize this lake? Those in Argentina recognize this lake? Yep, see, okay, so I chose kind of an area lake down here, and I just went and grabbed the data. And we do have, oh, you're there. Do you want me to just do this? You want me to just do it? Okay. Sure. Yeah, let's just run the QGIS example. We got a half hour. Okay, so we're gonna do the demo. The data for this little demo I think was provided in the update that you ran earlier. So the HDF file that we're going to put into QGIS should be on your computer, I think, right, Perry? We think. Data? Yes. Okay. So earlier we put this MODIS A1 granule inside of the GitHub repository. So when you ran your update, you should have this. So you could run this example as we're doing it. Okay, so why don't we try it? We're going to try it. This is a trial. We did not write a script for this. We said, it's the end of the day. We're going to wing it. What could hurt, right? What could go wrong? So we're going to wing it. So we're going to open the drag that file in. Can you drag that file in? Okay, so those of you who have a Mac, this may not work. And I will tell you why in a minute. Okay, so you got them all. Don't grab, only grab bands 1 through 7. Okay, so he literally just grabbed that file and dragged it into QGIS. Does anybody else want to try it to see if it works? Yep. So, and then we highlighted bands 1 through 7 because we're only going to pull in the bands 1 through 7 for this little test. Did anybody else get it to work? Raise your hand if you got it to work. Okay, we got. So it's this. If you go into this data file that's in that example, you see this file, you should just be able to literally grab it and pull it in. 1 through 7. 1 through 7. Yeah, that's bands 1 through 7. Everybody get bands 1 through 7 in? Hey, that worked. That's literally like 90% of what we're going to do. See how easy that was? It's so easy, even I could do it. So that's how easy it was. Okay. So if you were able to grab it and pull it in, do you end up with all the images in your domain? Okay. So you have MODIS data now in your domain. Okay. So we just pulled it in. Now, those of you we have one, who else has a Mac? So you could try it. It may not work. Oh, it did work. Okay. Oh, okay. So you're running, so that's different. So if you're trying to do this just on your Mac, I had to run a GDAL command to convert the HDF file to a GeoTIFF first, and then I pulled the GeoTIFF in. I don't know why. I tried it on 2 different Macs and it gave me the same error. And I think there's some sort of a GDAL bug on Mac. But there is a workaround. If you tried it and you didn't work, I could work with you on the bug, but everybody else here has Windows, so I think we're okay. Okay, so, but there is a little bit of a bug with the Mac GDAL. Okay. Okay, so I do not like the default colors that QGIS gives me for these images. Okay, so can you select image 1 and give it a different color band? Yeah, so if you right click on the layer, click properties, go down to the symbology, you can choose a different color band. So I like that one might work, or do the blue one. The blue, I like the blues at the top, at the very top. That one works. Apply. Okay. And then do that to band 6 also. You could do it to all of them. Okay. Did everybody see how he did that? I didn't even know how to do that. So he did something I don't know how to do. Yeah, so he modified the colors in band 1, and then he did a copy the styles and then copy style, and then just pasted that style onto the other 7 layers. Okay. I'm going to use that trick so much now. I normally most of my day is spent on Fortran code. I don't get to work on cool like GIS systems most of the time. So I'm still kind of a novice. Okay, but so I want to point something out when you get here. Okay, so uncheck all those layers except for 6. Okay, keep 6 in. So this is band 6. Okay, band 6 is the SWIR channel, shortwave infrared. Okay, and if you're looking at this image, what do you see can you see something pop out of that image? What do you see? You see the lake. The reservoir or whatever, yeah, it's a lagoon. Is it more of a lagoon than a lake? How deep is it? How deep is it? I don't know how deep it is. You don't know? Okay. But you can see the lake really pop out there, right? Okay, the lagoon or whatever it is. Go back up and check band 1. 10 meters. So that's a pond. I call that a pond. Okay. But so, if you look at band 1, you don't really see the definition of that pond or lagoon anymore. Okay. But you do see it in band 6. Okay. So we call that spectral differencing. And those spectral differences are what lead us to really come up with these algorithms, because we see differences in the radiative characteristics of water and land at different frequencies. That allows us to then play with band math to say, oh, I can use all these combinations to detect something like a lake in water or, in satellite imagery. Okay. All right. So we're going to run another test here. So we're going to do some raster or some band math. Okay. So to do this, do I need to slow down? How am I doing back there, by the way? Am I speaking? Oh, I got the wave. I need to slow down. Okay. Everybody able to get, I see some concerned faces like I'm struggling right now. Are you guys getting it, or are you doing something else? They're not even looking at me. They're looking at the beer menu for later on tonight. Did you get it? Oh yeah. Yeah, the colors. Yeah, I just chose the top. Yeah, that one. Then you should click apply. It's down at the bottom. Apply. Yeah. I think it's beyond her screen. So I think she's good. So we're going to play with the raster calculator here. Okay. So to do band math in QGIS, it's just you're using the raster calculator. Okay, so what we're going to do is we're going to play with the raster calculator. Is everybody ready for me to go on to raster calculator? If yes, thumbs up. Thumbs up. Okay, most everybody's thumbs up. So we're going to play with this. So we're going to do raster calculator. Okay, so if you go into raster calculator by clicking up at the top, raster calculator. Okay. The raster calculator comes up fairly. It's amazing. It does exactly what it's supposed to do. And if you look at the raster calculator, you notice that all those 7 bands that we pulled in are listed in raster calculator. Okay. All right. So I just clicked up at the top of QGIS raster. And then the first option was calculator. And that pulled up this window here. And once that window came up, all 7 of those bands that we just read in are in raster calculator. All right. And so here's how we can become remote sensing experts. Okay. So down at the bottom. So click down at the bottom. Okay. Now we're going to click, the algorithm. What's the algorithm? Remember the algorithm. The algorithm is it's green? No. What was the algorithm? Let's go back to the algorithm. Click back. Back up one. I always have to go back and remember. Okay, so it's green. So and the green band is what? Green band is band 4. Okay, so we're going to do, oh yeah, so band, I don't have a marker. I have a marker. So band 4. Band 4 minus band what? Band 6, I think. Yes, band 6. Over band 4. plus band 6. So that's what we're going to put down in that box. Okay, so we're going to go back to the GIS. So down in the box, if you just click on band 4, so you double click on band 4, it pops it down here. And then you enter the minus sign and then click on band 6. That's how you do raster math in QGIS. It's very simple, very straightforward. Now we're going to put the entire NDWI equation in here. So we're going to put parentheses around that, put a division sign in there, and now we're going to do band 4 plus band 6. Okay, everybody get that? Where are we at? Great. Let's run it, see what happens.
We should, but. Six.
Yep.
I see the division, and then I see band 4 minus.
No, it's band 4 minus band 6.
Yeah.
Oh, you have too many minus.
There's a dash in the name.
Ah,
Yeah, that's just the name. Yeah.
Now, we need to create a.
Oh, yeah. I'm sorry. Before you hit OK, because the OK button won't let you click OK until you give it a file name to write this to. You have to give it a layer name. So give it a layer name, like name it after your favorite cat. Okay. Or after your, whatever favorite dog or something, or whatever name you want to put in here, give it a name. And then you have to click on the 3 dots and tell it where in the file system to put it. Okay. So we're going to put it, in our data directory, and then give it a name of my first ever NWI layer, something like that. Okay. All right. So now that I have the file name listed in here with a file path, then all of a sudden the OK button is enabled and you can click OK. And you do not. You could, but I don't, sometimes I get an error. Okay, so you may end up with, if you click OK, you may end up with what looks like a gray box. Okay. If it looks like a gray box, I sat here and struggled with this gray box for about 2 hours until I remembered, oh, there's a threshold. We have to go back and look at the threshold. So if we go back to the slides, okay, go to my go to the one that has the threshold of 0.144 or whatever, 0.124. Okay, 0.124. Okay, so we're going to go back into my band math. Oh, wait a minute. Hold on a second. Go back here. On this layer, the layer that we made, change the minimums there to what's the threshold? It's 0.1. It's greater than minus 0.124, right? Yes. So greater than, yeah. So just put the minimum threshold of 0.124. Yeah. Just if you go right click, and set that minimum to 0.124 and hit enter. Click OK. Yeah, that didn't work. Why didn't work? It should have worked. It worked on mine. Maybe it's minus 0.124. How did it pull it in? Oh, it might be. Yeah, it might be because, so what band, go back to your slides here. So when I write this stuff down, I forget what I do. If you go back up. No, back down. Okay, so band 2, yeah, no, because it's SWIR. So band 6, SWIR is band 6, and so the NDWI is band 4. So, but the band 2 comes in when we do the partial surface water test. I don't know if I'm up anymore. So let's run through this. Hold on. Run back through that. Here, let me sit. Here, take this. So all right. We're gonna do this way. We're gonna run raster calculator. So this is, what was this?
That was it.
This is the one we just created? Oh, okay. So we're going to do if greater than minus 0.124, 1, we'll say 10, comma 0. And then we're going to give this a new layer. Mogwai underscore NDWI 2. And we're going to put that here. And then we're going to, where am I going to put that?
Does it matter?
Yeah, it doesn't.
I'll do desktop.
Desktop? Okay. Try that. Ah, it worked. Okay. So this is, I'm going to, the threshold, we forgot I had to put the threshold in there. So let me show you what I did. Okay. So the cool thing, and I had to Google this to learn it, right? About QGIS, because everything you need to know in life, you can learn on Google. So in the raster calculator, do that again. We're going to do what I just did. So I should have nested it inside the algorithm. You can put if statements down here at the bottom in this calculator expression. So what I did is I said if, and you have to do if first, if parenthesis, the array that we created up here is greater than minus 0.124. Okay, close parenthesis. No, wait, comma. Then after the comma, then you say, this would be your true value. If this test is true, give it a value of 10 or something, or whatever you want, 1,000,000. You can put anything in there. If it's false, then that's when you put the second value in, 0, minus 9999, whatever you want. Okay. Close the parenthesis. Okay. Yeah. So that's how I did it. So it's basically, we're doing band math, but you have to do an if statement in here because we have to give it the threshold. Okay. Everybody understand that? Understand how I did that? What did you get? Did it work? You got an error? Uh-oh. Yeah. Okay, we're almost done. All right, so we're gonna, unfortunately, because of time, we're gonna speed past this, but that's how you nest band math algorithm inside of QGIS. So what we calculated with this test here was that first, Mogwai test, which is the normalized differential water index. That's a majority of the test right there. And when you do that, okay, oops, When you do that, you should get a layer that looks just like this. Right? And that's what I just calculated. And notice how the water pops right out. Okay, so I'm going to zoom in on that water. Anybody ever go to this lagoon or pond or whatever and do some fishing? No, or I don't know what you do out there, but I'd fish. But so anybody know about, anybody been out to the Chiquita Laguna? Does it look like this? Does it look like that? Okay, I hope it does, because if you compare it to the satellite imagery or to the just the the ground imagery, it should look somewhat similar to what we have. Of course, we don't actually have the satellite imagery, we just have a map. And I know from looking at it on satellite imagery, there's deeper water and there's more shallower water up north with a lot of sediment coming in. Okay, you could see that in the satellite imagery. So this map that we produced looks fairly similar to this water imagery. Okay, so that's how you detect water area essentially from space, from in satellite imagery. And then because this becomes just a binary map of ones and zeros or tens and zeros or whatever you did, you can just write a little reference that says, for every pixel that has passed my test, add up the area for that, and that's the area of my lake. Okay, and then that's how, when you can compute that area, then if you have the bathymetry, that's how you get your volume. Okay, so we have a product. If you go get satellite imagery from other times, you can compare images. So I went and got imagery from 2005. Okay, and compared that with imagery from 2000, this is this year's 2022. So, and I didn't necessarily do this in GIS yet. I was just doing this in some other software, and the outline of the lake is in black here. So this is the outline of the lake in 2005. This is the outline of the lake now, which is much closer to where the surface water is. All right, so you can see the differences over time by looking at multiple years of satellite imagery together. All right, so this is basically July of 2005, and this was July of this year. Okay, so it's been in a drought here, obviously. The water, there's a lot less water than before. And so it's nice to be able to do that on an annual basis. And if you can create a process that automatically does this, then you can either in a GIS system or in Python code, which uses some GIS under the hood, GDAL, then you can calculate that in an automated fashion and then nest that into a web page that has a bunch of lakes on it. So I pulled in our real-time product from a couple of weeks ago. Each one of these green dots is essentially, an area where we're calculating an area for a water body or something like that. Okay. And so I just went and clicked on Chiquita, and this is Lake Chiquita Laguna since early 2000s. And this is the water area over time. Okay. And so you could see, drought, back in 2013, 2014, right? And then this is the current drought. So it gives you a nice ability to measure the impacts of that drought from space by looking at the area, the water, essentially your water area. Okay. And this is literally just with the satellite that we've downloaded from Earth Explorer that you can do. So you have access to all the same data. All right. And then you can calculate statistics with this. So we have statistics based on all that data. This is the average area of the lake. And this is the max and the min that we've seen from satellite. Okay. So you can calculate simple statistics. And then you can do that either from a monthly or a seasonal type basis. So by doing that, you get a very good value. And then again, my purpose would be to take that observation and put it into something else, but somebody who's just interested in water resources could use that alone. Somebody who's, just tracking drought or something like that, could use that. Power plants might be interested in, because, oh my gosh, my water area is getting below this amount, and that means my water intake pipes for my cooling plant is bad. I mean, there's a lot of possible applications to a product like this. Okay. Questions?
It's not only for water. You already mentioned, but I want to get it clear. It's not only for what liquid water, it also detect snow water. Because in the Andes, in the Andes region, it's put it like a true.
So one of the reasons why I run a snow flag through there is because we filter the snow out for this particular test so that we don't flag snow water. There are very similar tests for MODIS for detecting snow. NDSI, the normalized differential snow index, which is very similar to NDVI and NDWI, also can measure snow, and they filter out water to measure snow. Very similar type tests. But for ours, we filter that out because sometimes they're false. That may be a high reflectivity from granite or something else sticking out. Okay, so we'll generally filter most of those high mountain peaks out before we do it. So, and we also run the NDVI algorithm through it. So in the back.
Thank you. Thank you. Can we use this algorithm for flood extent?
Yes.
Also?
Yes. And that's one of the values is if you can see the flood extent. So the challenge with using optical imagery to measure water is it has to be clear or mostly clear to be able to see the water. Okay.
Sure.
And so we know often if you're flooding, you're cloudy. Right. And so unless it's a big convective system that comes through, rains a ton and then clears out, then you can probably do it, post system, post hurricane, you can use it if it's assuming it's clear. But as long as it's clear, you can map surface water, and those partial surface water tests will help you map it in areas where it's vegetated. And so you'll get some of that surface water. Since it works in the Everglades with vegetation, it can also work in areas where it's other than vegetation, such as urban or suburban or just, along the river. Okay. As long as it's wide enough so that MODIS can see that large of a river. Okay. And when I was doing some of my tests, some of the other granules I downloaded, the Paraguay River, I could see some pixels for Paraguay River. So it might be possible, especially if it's a large flood, to see those pixels from in MODIS. If not, you can run this on Landsat. So you can run on a higher resolution satellite data.
With the same thresholds.
Yes, very similar, very similar. We adjust them up and down a little bit. Okay, but those thresholds in that paper that were published on that first page, those apply to Landsat, and then we nudged them a little bit for MODIS. Okay, but not a lot. Okay. Any other questions? I have bored you to death. Is everybody still trying? Is everybody still trying? Are you guys trying to do this? You're still trying? Okay. This tool, I was going to get, so I ran out of time. I can't give you the demo. If you'd like to see my real-time one, I can show it to you. But yeah, I have a real-time one. It's not available on the internet. It's available on the internet to a few people. I can't, because it's on one of my sites. It's sometimes our sites we can't make them public for some reason, but I would like to make it public because nothing in here is proprietary or anything like that. It's all easy free code. But I run it on a website all over the world. So yeah. And it's actually fairly lightweight. It just runs on a fairly lightweight little cluster Linux computer. Okay. Question.
Ay, pero en español, Leo.
Oh, Sole. This one on? Is that working?
¿Hay algún producto derivado en base a lo que mostraste ya que permita conocer el volumen almacenado en los reservorios?
The elevation,
Sí.
the elevation.
No, de volumen.
Okay, so this product gives you an area. If you know the bathymetry, if you know the depth, or at least if you have an average depth of your reservoir, then you can essentially generate the volume value to come up with how much water is stored. Sometimes in some places where you don't have good bathymetry, there are other satellite products that give us satellite altimetry of a reservoir, so we know what the top level is of that reservoir, okay, or lake, and we can use that top level of that lake or reservoir to put and calibrate a model. But in order to get the volume, you have to know your bathymetry. Okay, so you have to know what your average depth is and the area of that, combined with the area of that lake, to get at least some rudimentary value of what your actual storage is. Okay. Do we need to redo the bathymetry every so often? It depends on the sediment load on your water, on your lake, and how much the lake is changing over time. So if you have a high sediment load coming in where you're getting a lot of deposit into that water, then yes, you would have to update that. If the amount of sediment coming in is similar to the amount of sediment going out, or if there's some active dredging program so that the sediment is being removed on a semi-annual or on a regular basis, then probably not. Okay. Or, if you know what that change is over time, then you can probably estimate that. Okay. So not every year though, maybe every few years, and there are easy ways to get bathymetry if you don't know it. There are sensors like submersible sensors you can drive around to just take altimetry readings of the base of the bottom of the lake. I've learned about some airborne sensors that with different types of lasers that can measure bathymetry from an airplane. You don't necessarily have to do a really expensive project in order to get bathymetry. Okay, as long as it's not a very deep water. Any other questions? Okay. Is it beer o'clock? Yeah. See? Okay. I think we're done with this for today. So do you want to say something? Are you wrapping us up? Okay. Okay.
Vale, entonces eso sería, cerramos la jornada del día de hoy. Un fuerte aplauso para nuestros instructores del día. Bueno, y como decía John, evotranspiración pasa para el día de mañana, por la mañana. Entonces, el único recordatorio sería que por favor nos ayuden rellenando el Padlet que se les compartió. Ya se les mandó por correo al equipo, a las personas que están en el Zoom. También ya fue compartido por el chat, así que nos ayudarían muchísimo. ¿No se les ha compartido? Vale, se les va a compartir para que nos ayuden a responder. Y bueno, mañana empezamos siempre a las 9 de la mañana. Y bueno, muchísimas gracias por su paciencia y entusiasmo en toda la jornada. Gracias.